So you two must have both felt pretty okay about the questions because I got about the quiz.
Yeah.
It's just filling in those four reactions, right?
Yeah.
And the only one you really had to watch out for was the primary alcohols with the chromic acid. Did I not? Let me do that real quick. Yep, I got it all set to do that, and then I didn't finalize it. Hang on 1 second.
Keep on doing it. It'll be a whole slide. I have your
Oh, it does. It's actually one of the fun intersections between OChem and biochem.
Okay.
And actually Gen Chem when we talk about buffers and weak acids and weak bases. All of that factors together. But let me do this before I start talking about that because I can't talk and navigate the website at the same time. Nope, it's not in my wheelhouse. All right, if you refresh week 9, you should be able to see it now. All right, so where is this is the one I want to start with. One of the more important parts with brewing beer is the way that it works is that you need to take the starch that's present in barley or in some sort of a grain, and you need to convert the starch into a form that yeast can digest, because yeast can't digest a starch. It doesn't have the necessary enzymes to break it down into sugars. So the first step in brewing is you take the grain and you put it through what's called the mash, which you may have heard the term before. What a mash is doing is basically steeping the grains, almost like making a tea out of the grain, but you have to do it at a certain temperature and a certain pH, because the whole point of using, and it has to be a specific grain. You have to have some amount of malted barley present or something that's been malted, because malted means basically they took the grain, because the little grain particles are basically the seeds of the plant, right? And so they have all the genetic information and all the protein necessary to start growing. And they have all the energy, but the energy is all present in the form of starch. What you do when you malt a grain is you basically let it start to sprout, and then you stop it by roasting it. By letting it start to sprout, you get it to start producing these enzymes that start breaking down the starch. But then before it can actually break down the starch, you kill it essentially. But the enzymes are still there. So there's that creates a cool situation where if we want the different enzymes to still be active, there's these two enzymes in particular, the alpha amylase and beta amylase are the ones that break down starches and turn them into sugars. But they're only active at a certain combination of pH and temperature. So the x-axis is pH and the y-axis is temperature. So this is in Fahrenheit, and we always do everything in Celsius, but for whatever reason, all the brewing stuff is still in Fahrenheit. So I know all my brewing temperatures in Fahrenheit. But basically, you want to hit about 150 Fahrenheit. You want to keep it there, and it has to be in this red pH, or else the enzymes are denatured and they don't work. So basically, by controlling the pH and the temperature, we control which of these enzymes are active. And the most important ones are the green ones. The other ones have some effect as to some amount of taste and how much nutrients the yeast will be able to use. But we basically need to be sitting right there for an extended period of time to let the enzymes do their work. Now, the trouble with this is that you might notice this is well under the pH of drinking water. Drinking water usually between about 7.5. And tap water has minerals in it, and what they call residual alkalinity, which is basically drinking water is buffered at that 7.5 pH because it's got magnesium ions and calcium ions and carbonate in it. And so the amount that it's buffered depends on where you get your water. And so that's where water quality really comes into play is how much do we need to shift the pH to get it here? It'll shift on its own naturally. The roasting process actually produces compounds when you malt the grain. It produces compounds that actually will drop the pH into the acidic region. And the darker the grain is, the more roasted it is, the more it shifts the pH. So basically you can't start from DI water and then make it dark beer because the dark grain will actually shift you well into the pH of 4 region. So you actually can't convert all of that starch to digestible sugars unless you go to your DI water and you come back and you add some minerals to it to basically act as a buffer. So that so historically they didn't understand what was happening with the enzymes, but back in the going back to the 1600s and earlier, they knew that certain waters made better types of beer or better suited for certain styles of beer. So that's why Dublin has Guinness. It's because you couldn't make a light beer with the water that you had in Dublin.
Because it had too many.
It had too many minerals. It had to make a dark beer with it. In places, the darker grains, right? And so there's actually there's a lot of different graphs. I kind of like, this one's complicated, but it's actually a functional graph. It's called a nomograph. This is one of the best authors who writes one of the best books about how to homebrew beer. Basically, you go to your local water quality source or you do your own testing and you figure out how much magnesium and how much calcium, those are the two most common things in drinking water, are in there and what your pH starts at. And you basically, so this blue region is where you're likely to find your numbers from tap water in the US. And so if you say, okay, I've got that much magnesium and I've got this much calcium, then you draw a line between them. Where it hits on this line, you then compare it to how alkaline your water is, what the starting pH is. So let's say if it's fairly alkaline, might have it like that. Then you draw a line there, and that tells you what color of beer you can make with that water. So if you want to make, I want to use this water to make a lighter beer, I need to do something to shift this further over. So basically I can add hydrochloric acid to it. You add HCl to it or citric acid or something, this line shifts over, and now you can make a lighter beer. So you have to treat your water based on where it starts and the type of beer you're trying to make. But it's an ongoing thing. So brewing has a ton of chemistry in it. It's got a lot of water chemistry, obviously. But it also, you have to understand which enzyme, the alpha amylase versus the beta amylase, make different mouthfeels of beer. Beta amylase, I might mix these up. I want to say alpha amylase starts at the end of the chain and works its way down, versus beta amylase will just chop it randomly in the middle. So with beta amylase, you get more like random chunks of small starch molecules. They give it more of a sweet taste because the yeast can't digest those as much. But if you wanted to favor a lighter beer that had less body to it, that was more watery, then you would want to favor the alpha amylase. And so you would do it at a different temperature and a different pH to get to the right spot on that first barrel.
So I remember saying you move for the water molecule to stop making beer.
Yes, so that's the other piece, is the reason you can't usually just use tap water without further treating it is because tap water is treated with molecules called chloramines. So it's basically a nitrogen attached to chlorine to sanitize it. And our tongues can't detect chloramine at very high levels. It's in the 4 parts per million is about the threshold for where we could taste it. And so as long as tap water's under that, you can't taste the chlorine and it tastes fine. The problem is if you let even those small levels of chloramine be exposed to the phenols that are present in the malted barley, they make chlorophenols, and our body's much better detecting chlorophenols. We detect those in the 1 part per billion range. So just because water quality is good enough to drink, it's not necessarily good enough to make beer with, because we start making these other compounds that start tasting plasticky, basically. It's kind of gross, but the flavor that gets used most often to describe what chloramines taste like is like a Band-Aid. It's like that type of plasticky. I don't know, like if you think about the smell when you first open a Band-Aid, it's kind of like that's the taste in the water if it's got chlorophenols in it. So basically, if you want to use tap water, you either have to remove the chloramine by basically pouring 5 gallons of the water and then letting it sit for 24 hours, or heating it and then cooling it back down before you start brewing with it, or you have to buy distilled water from the grocery store and then make your own. Because if you get your own, you can add magnesium in the form of Epsom salts, because that's just magnesium sulfate, and gypsum is calcium sulfate, or you can get calcium chloride. And you can basically make your own water profile starting from DI water. And then you can make whatever you want. But that's a whole nother step, and it's another cost as well, and things like that. So when I stopped being able to use the tap water because they started chlorinating more strongly up here, it kind of correlated with when I stopped brewing beer. Well, there were a lot of other, that's also the same time that we bought a fixer upper and Valence was born. So there was a lot of things going on. It wasn't just that. So you can do it with, if you don't use grain, you can malt other grains that don't produce gluten. And the other thing you can do is you can buy alpha amylase just as its own enzyme, and you can add it to water, and then you can do this with rice. You can make beer entirely with rice. It's not technically beer. If you do that, it's some form of malt liquor. Basically, it has to be at least 51% malted barley for it to be considered beer. And in Germany, actually, you can't call it beer if it has anything but malted barley in it. Beer in Germany is only allowed to have 4 ingredients: malted barley, hops, water, and yeast. Interesting historical. That's the oldest food quality law in history. Is called the Reinheitsgebot, which stands for German beer purity law. So fun history fact there. Sorry, you had your hand up too.
Yes. What about water that's like fluoridated? Like I know a lot of tap water now is fluoridated with that.
Not really.
No, like it'll be fluoridated too, but it has fluoride in it.
So the fluoride's present in smaller amounts. The fluoride's less reactive.
Okay.
And the fluoride's there just for your teeth. But basically, it doesn't react with anything other than your teeth and bones, basically. So fluoride doesn't affect anything, as far as I'm aware. I never read anything. I never actually looked into that because nothing ever said watch out for fluoride. So it's possible it messes with things, but I would think I would have read something.
Okay.
Because I was pretty immersed. I ADHD hyperfixated on brewing beer for about 5 years when we first moved here.
Yeah.
And to the point where I had to teach an upper division beer making class in the chemistry department at SNC. And we covered all sorts of stuff like this. So I feel like I would have seen something about fluoride if it was a problem.
Yeah.
Good question though. All right. Back to obviously, if you ask me sciencey questions, you two now have the science. Like I can't start with that explanation when my 100 students ask me about beer.
Yeah.
But you have the proper background how to actually be able to understand that.
Yeah.
How do we know when a ring will be opened or stay closed? It depends a lot on what the ring is, because basically you don't do ring opening reactions when it's all carbons in the ring, unless there's something like ozonolysis or something going on, right? So it's more about just, we don't always think about the ring opening reaction. The one you should always be looking for the ring opening reaction is when it's a three-sided ring, because those are really unstable.
Yeah.
Beyond that, it's more about what the functional group is, more so. And usually the ring opening reactions will have something as part of the ring that's not a carbon, unless there's ozonolysis involved. So those are what we call heterocycles. Heterocyclic rings are anything where you've got something that's not a carbon as part of the ring. I remember two of my friends in undergrad studied abroad in England. Basically, if you wanted to stay on track and do a study abroad at my school, you had to go to an English-speaking country because you had to keep taking your chemistry classes while you were doing it. And so their OChem 2 class they took it in England, and it was a class on heterocyclic chemistry. So specifically, how do you make these, use them, and break them apart? So it is its own field of study. Because they do behave differently. A lot of pharmaceuticals have heterocycles in them. But it's not something where we don't need to worry about it specifically at this point. It's just another skill in terms of make sure we don't lose a carbon somewhere. There we go. All right. Do we have any questions about any of these specifically?
Was there one that you had expected?
To be honest, when I saw that both of your questions were not about this, I figured you both had it under control, and I didn't look at your answers yet.
Yeah.
I tried to create them last night, but neither of you had it turned in last night. Yeah, I looked at at about 9 when I was sitting on the couch doing grading for my other class, and it was there's like, they're fine.
You're probably doing it like that. Probably.
Yeah, I started. No, any of those 4 that we talked about would work. The H2CrO4.
H2 on top. P2 or ED or NI for E. I just don't know if you're expecting this to be example or if you're expecting this to be.
Oh, so that one is less commonly used just because that's the one we have to get it out to like 300 atmospheres and really the temperature to get it to react. So it'll work. But that's the 4 that we talked about were the desmartin triadenine, the DMP, the PCC. I'm trying to think what the name of the other one, the Bell-Hardman.
We won't know the name.
That one needed the CMSO. Volstrucker, I think was the name. Those are all more commonly used for reducing the carbonyls just because of the reaction conditions. So I was not planning on you using any of the hydrogenation version, but it's not a wrong answer. We did talk about that, and that is a valid way to do it. Unless you're doing industrial chemistry and you have the ability to get up to 500 atmospheres and 500 Celsius, it's not really practical though.
You just told us to try not to.
Yeah.
So I was trying to not repeat them. Where I said.
All I really meant by that is don't go through the entire thing and just say PCC, 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 PCC. Like you could do that.
Right.
And it wouldn't be wrong. All right. We're going to continue on with alcohol reactions, and we're going to switch into other oxygen containing compounds here in a few minutes.
Well, I want to have notes that say focus on top. So the Na2Cr to go to 7, would that be a color for the
I knew I should have left that slide in. Hang on, let me pull up that summary slide at the end. The Swern oxidation, that's the one I was talking about. So these are the 4 that I was thinking you would use. You can do oxidation with chromic acid. Oh, sorry, the one you showed me, the drafting about, that was a reduction. There were 2 reductions. Yeah, this one is a pretty common. All 4 of these are pretty common options. For the
What about the lithium one, the LiAl?
so for I'd forgotten that there were 2 reductions here. So for this one, either lithium aluminum hydride would work, and that's a common one. But more common is the one that we're going to use today. Sodium borohydride, just because it's less angry. And we could use it on this one too. Or you can say with the aluminum hydride, or like you did, the hydrogenation option works as well. It's just less common. Okay. This one is one you practically use this one if it's an acid or an acid derivative. If both of these, there's an aldehyde and a ketone, so you can use sodium borohydride for EAN. Would be fine. And all of these, this one you got to use chromic acid.
So really the only one around these two.
Yeah. We try to avoid using this one because the chromium, but it's the only way we have to get to an acid. So. All right, let's talk about substitution of alcohols. So we have 2 cases, like we've seen before. Tertiary alcohols are kind of their own thing. The tertiary alcohols are harder to make because we have to use that Grignard reagent to do it. We can't just reduce an aldehyde or a ketone. We have to produce an aldehyde or a ketone with a Grignard reagent to make it. If an alcohol is tertiary, we want to change the alcohol back to being a halogen, though, it's actually easier because we can go through an SN1 reaction. So remember, tertiary alcohols, because they're tertiary, that oxygen can leave pretty easily. If we do this in strong acid, we just wind up. So we use bromine, for instance. We can just protonate that oxygen. That gives us a really good leaving group. And because it's tertiary, it's easy to leave, right? We only saw SN1 reactions when it was tertiary. So that leaves as water. We get the tertiary carbocation. And then our bromide can come in here and attach. So if we wanted to convert a tertiary alcohol to a bromide or chloride, pretty straightforward. or even an iodide. We wanted to add an iodide. The problem is, if it's primary or secondary, we can't make this carbocation very well. Primary and secondary alcohols don't really go through SN1. So since they don't go through SN1, if we wanted to do the same thing, if we wanted to take this molecule and convert the OH to a bromide or a chloride, it has to go through SN2, which means we need to work on making it a better leaving group, even in water. So both of these versions, if we're going to chlorinate or brominate, we're going to go through a step where we turn our oxygen into a better leaving group. And the end result is an SN2 reaction. So remember also that the SN1, we're not going to preserve any stereochemistry. If our R groups are all the same, then we don't have any stereochemistry to begin with. But if we had like a methyl, and a propyl, 3 different R groups, that's a chiral carbon, but we lose that chirality, lose the stereospecificity when it goes through that planar intermediate. These other ones, though, we can go through an SN2, we can keep that stereochemistry, well, invert it. Because the first step for these, so if we're trying to chlorinate something, we're going to use SOCl2, which is just going to look a lot like that DMSO molecule we dealt with last week. What's going to happen is basically that the sulfur oxygen bonds are more stable than the sulfur chloride bonds. So we're going to replace the sulfur chloride bond with a new sulfur oxygen bond instead. So your oxygen lone pair attacks the sulfur. And in doing so, you break the sulfur oxygen pi bonds to make this tetrahedral intermediate for a second. And then, similar to other reactions we've seen in the past, we're just going to kick off the leaving group and reform the pi bonds. And once we do that, it does a little bit of a rearrangement. No.
But
it can't be tertiary because the steroids. There's not room to bring this big sulfur chlorine molecule up close to tertiary alcohol. And then the almost the last step is once we reform that sulfur oxygen pi bonds, we're just going to deprotonate what was the alcohol. Because now we've got an oxygen with a positive charge. So we just need something that can act as a base. We usually use this PY, means pyridine. Pyridine is this molecule. We just need a relatively good base that's not going to cause it to go through any elimination reactions. So we need a moderate base. And pyridine has several advantages, one of which is that it's already a solvent. So it makes it easy to do this reaction. And then 2, it's not going to force any elimination reactions going. It's not that strong of a base. Then once we do that, we get this SO2CL, which is a really good leaving. So then it makes it pretty easy for pretty much anything to come in and be a good nucleophile. Chloride is an okay nucleophile. Now that we've converted the oxygen into a good leaving group, we just do it in SN2 stepping.
Oh.
Something that says.
Oh my goodness, we started using not old, but like thing equations that I learned in Gen Chem and physics yesterday for the variance. It's like I thought I was done.
I heard Bruce like he was talking about heat, right? So we're using Q. Q
Yeah.
equals mass times CP times delta T.
So I was nice to take those together. Physics and Gen Chem.
All right, so the tricky part about this mechanism, the only thing that's really new here is the way that we're converting the oxygen into a good leaving group. And it's a similar mechanism to what we saw before we looked at the reduction of the carboxylic acids. You attack something that's at the other end of an oxygen double bond, and you break the double bond, and then you reform the double bond and kick off the leaving group. That's a fairly common. I think in art and literature they call that a motif. It's a pretty common pattern that we see in organic chemistry. Take something trigonal planar, it's sp2, break the pi bonds, and then reform it. Okay, so the bromine equivalent is even simpler. If we want to brominate something, we're still just going to take a bad leaving group and turn it into a good leaving group. We're going to use phosphorus tribromide though. And a phosphorus oxygen bond is more stable than a phosphorus bromine bond. So exactly. Same exact criteria. It's just if we wanted to add bromine instead of chlorine. So basically it's two SN2 reactions back now. First SN2 is your oxygen attacks phosphorus and takes off the bromide. And then the second one is your bromide comes back and attacks carbon and takes off the oxygen.
I found what we're doing. The mechanism like on arrows. Right. Yeah, so you buy it, so I don't know it's gonna be good. I think probably next. Like what's the you know arrow piece?
That versus that. So let's practice. Draw them out again. And then draw that othermost piece that we were talking about for the same one. Your hydride patches, you break the pi bond, reform the pi bond, kick off the leaving group. I'll give you a few minutes. Head start on while I go fill up my water bottle.
The oxygen as the force. Then the over the top.
Always have that pulsing hum. Just never noticed it until now.
I always hate when I have done those. Right after. Cause then you can never ignore it again.
Yeah, let's can't unhear it.
Yeah, exactly.
Alright, so this first one is the trickiest one. Oxygen attacks the sulfur. Sulfur oxygen pi bond breaks. We get this tetrahedral intermediate for a second. Then it boots off the chloride and reforms the sulfur oxygen double bond. Now we've got an oxygen with a positive charge on it, so we just deprotonate it. That's what the period is for. I would prefer to see you draw the structure for the pyridine, but it's also not uncommon for people to just write it as PY and then just draw a little pair to attack it. So if you, worst case scenario, you forget structured pyridine on the test, just do that. So pyridine deprotonates it. Now we've got a really good leaving group. So then we just do an SN2. The chloride that we kicked off with the sulfur earlier comes back and attacks from the opposite side as our leaving group. So we invert stereochemistry and we get our product plus SO2Cl, which is going to have a negative charge on it. Try B yet? Okay, that's fair. So I'll give you a minute to do B. So, and I'll remind you verbally, B is just two SN2 reactions in a row. The oxygen attacks the phosphorus and kicks off a bromide, and then the bromide comes back to attack the carbon and kicks off the oxygen. Give that a try, then we'll work through it. Okay. Oxygen attacks phosphorus. Suppose I did leave a hydrogen off there. That's our group leaving group right there. We're done. So then it's just the bromine comes around, does the backside attack. Plus a POBR2, whatever that would be called. I don't even know what they call that, but. So similar idea, make a good leaving group, then do an instant two. It's just making the good leaving groups even shorter here.
See,
Yes.
I don't know how to get rid of the oxygen on top. Like I did basically one round box, like the double bond oxygen. Wait, still have and that's still that really was wait now. I don't.
So first step is hydride attaches here. You bring the 5 on, right? This is the one that I did the caveat at the beginning of Thursday's lecture.
Okay.
That it makes. I originally said, oh, it just makes a good leaving group because this is a good leaving group. But it's not a good leaving group unless you're under acidic conditions or under basic conditions. So what happens instead is the aluminum here. And then so we get something that looks like. So our first intermediate is going to look like this. We added a hydrogen here. Then we have that ALH3 still floating around. Yeah. Let me back up. Actually, we'll just do. So the first step is the hydride brings the electrons with it and attacks the carbonyl carbon. So that's what this hydrogen is. So we broke the pi bonds and attached the hydrogen. Then the next thing is this aluminum doesn't have a complete octet. And so it makes a really good target. So we just basically attach our aluminum there. And now this is a really good leaving. So the oxygen takes that and you reform. Carbonyl group. Bring it back over this way. Now we have the alpha. Yeah, because it's a. I was trying to spell it different, but it's still there though. Sorry. No, I was just checking the more the better drawn mechanism.
But not
And now not yet. Yeah, that's exactly how it is. I was double checking my work as well. So now we're gonna come in. Now we saw an outline that still needs to be reduced to the rest. We're trying to end it, you know. So let's do it again. We still have more aluminum hydride. So hydride attacks the carbon again. Breaks the 5 bonds. Now we've attached 2 hydrides, reduced that carbon twice. Now we're going to bring the water into proton source. And because this oxygen doesn't leave, we're just going to propane. So there's actually 2 recurring motifs. One is attack something that has a pi bonds to make a tetrahedral intermediate and then reform the pi bonds. The other recurring motif is we had to make this a better leaving group. And we made it a better leaving group by just attaching the aluminum to the oxygen that's going to leave. So the aluminum that has the methyl group attached. And then once we get to the aldehyde, then you can go back into our normal methods. So all of our hydride sources, sodium borohydride is the same thing. And the sodium borohydride version of this reaction is exactly what we're going to do in labradorite. We're going to reduce a ketone, fluorinone, which the actual procedure is not all that different than a lot of the procedures we've done before. We're just using different reactants. Say it's fluorinone. So it's just a ketone that we can reduce to be fluorinol, probably, be how we would name it. We're just going to take that carbonyl there, attack it with the hydride at the bottom, then add water, and that's going to give us the alcohol instead. That's not the one I wanted. That's what I was looking for earlier. Couldn't find it. I've got too many tabs open. All right. So let's take a break. We'll come back and we'll start talking about ethers.
that was time.
Let's say we got one today.
It literally, I think, because they all use like green brown. They're using Starbucks, so I'm sure it's sweet. I know when it's green brown, it's fine, so we work back to it.
Okay.
No lab. Yeah,
Um,
I mean, I do have,
is it not an inflammable cabinet?
I look through everything.
Because we had it last year, right?
Yeah, and I always, like, whenever we run down.
Yeah.
Of something, I always buy it like right away. So.
Yeah.
Okay. And so, it's like, it is really expensive. I think it was a lot of these things. But. Is due to it, don't have.
That's so weird.
I mean, I have to our exam on Monday, so she's not likely, but
We'd have to do some sort of paper and finish last week's assignment. I mean, to be completely honest, I have a migraine today anyway, so I'm open to that.
Yeah, let's just finish last week's thought. Day 3.
Smells good. Nothing like the smell of popcorn. All right. Well, I'll think about what we're gonna do with that. That is a good one for you to spend some time doing, answering the questions, thinking about it. So.
Okay.
All right. Let's cover a few more reactions of alcohols. Let's try and get through this. We know about elimination reactions to some extent. So this is partly just review, because we already know that the tertiary alcohols, especially, can go through an E1 mechanism.
So tertiary alcohols.
Tertiary alcohols are the only ones that you'll see E1, because you have to have that leaving group leave first to get that carbocation intermediate. And so that just looks like this: concentrated H2SO4 with heat. Remember, we need the heat to change the which side of the equilibrium reaction we're favoring, right? Because we have that delta G equals delta H minus T delta S. Elimination reactions have more entropy. So entropy favors the right-hand side, but enthalpy, the bond energies, favors the left-hand side, because single bonds are more stable than double bonds. So this is one of the ones where we can control which side of the equilibrium reaction we favor by just changing the temperature, because higher temperature makes the entropy more important. So we have to do this with heat, because we're going to get two different products here. So entropy favors the right hand side, so heat that favors the right hand side. The other way we can go about this, and this works for more than just tertiary alcohols, this works for any alcohol, is this is another style of make it a better leaving group. We saw this. This also opens up the alcohol to other substitution reactions as well. You remember seeing this tosyl chloride back from Open 1. Yeah. We didn't do a ton with it at the time because we're more focused on the halogens at the time. But basically what we can do with this tosyl chloride is it's going to attach to the oxygen here, make it a good leaving group, and then we just need a strong base. So the OTS is going to be our good leaving group, put it with a strong base that can grab hydrogen from over here. Yeah, leaving group leaves, the carbon and hydrogen electron turned into pi bonds, and we protonated our alcohols. Right, so this is going to be our E2.
So tertiary alcohols can do.
Tertiary alcohols can do E2. This works better with primary and secondary though, because of the sterics. This is showing tertiary as your example. E2 works better than SN2 for tertiary because we don't need our nucleophile doesn't need to get into this carbon in the middle. It needs to get to one of the adjacent carbons, so it's not as crowded as it looks. So this version is the one that, if I was going to pick one of these to remember for the sake of synthesis, I'd focus on this one because this works on any. And in fact, by changing up our base in the second step, we can favor the Hoffman versus the Zaitsev product. This is going to naturally form the Zaitsev product, the more substituted alkene, but we can get it to make the less substituted alkene if we use the TBOA.
So this specific, the TSCL also were for primary.
Yes. And just because I don't have the actual structure here, so give me a second, we'll pull up. So tosyl chloride looks like this. So its full name is polyamine sulfonyl chloride. Basically what happens is the sulfur attaches to the oxygen. So similar to what we saw with the SOCl2 2 slides ago. And that's just going to make it a better leaving group. It's just instead of coming around, and it doesn't make it such a good leaving group that it leaves immediately. So you still need a pretty good nucleophile to come along, or a decent base to come along. So this is why we use tosyl chloride, gets used for elimination reactions, and the SOCl2 gets used for substitution reactions. It makes a good leaving group, but it's not too good of a leaving group.
So this you can use your elimination.
Correct. And Riley, you still have, did you finish all your melting points? Oh, they're all wrong.
But I already.
So maybe what we'll do to make this so it's not just a wasted lab, is just have you do it. That makes a lot of sense then. So I know you still have like 4 left to go. 5 melting points takes a bit of time. And then you can answer the questions and work on that together too.
Yeah.
Okay. We'll plan on doing that then. I'll go tell Marilla so she's not freaking out there.
Don't need socks. It's a sticker on this one. But I'll do on the give up your comments.
You know, sorry, for the one I said maybe we'll do that, but I don't know if she is. No, I have her number. I'll text her. Thank you. All right. So if we have a situation where we don't want an alcohol to react. So there are some cases where we want an alcohol or one part of the molecule to react with not the other. We use what's called a protecting group. So the protecting group is basically we're just going to convert reverse convert the alcohol to something that it doesn't react. And so we use this TMS group. It's not the same TMS that we use in NMR. That's tetramethylsilane. I don't believe this is tetramethylsilane. But basically, the net result of it is we stick it onto the alcohol and it gets converted to this OTMS group, which then we can kind of do whatever we want with the rest of the molecule. This OTMS group is really non-reactive unless you expose it to this TDAF, which basically undoes that TMS.
Is it always connected with chlorine?
Starting, yeah, that's what makes it reactive.
And is that always what we're gonna use for?
That's the most common one, yeah. There are other ways. So most functional groups have some protecting group that you can use that'll basically render it less reactive. So TMS is what's used for alcohols.
Is it always gonna be over the ECN? Or?
Yeah, you need this. This is triethylamine. You need the triethylamine as a sterically interface.
But it should be over something.
No, you won't see it that way. All right, so this is just one example of how this could work. If you had the bromide, if we just expose it to magnesium, then aldehyde, there's other side reactions that can happen. But once we protect that oxygen, now we can do a regular Grignard reaction where it's going to be your first intermediate after step one. It's going to look like magnesium, bromide attached, OTMS. And then we expose it to an aldehyde, then this is just an example of why we use it OTMS. Because we don't want the alcohol. If we left it as the alcohol, we try to do this reaction. The Grignard reagent will react with an alcohol. And we don't want that. So to prevent that, we protect it, turn it into a less reactive group, and then we can do our regular Grignard reagent where we add all this together. And then the magnesium bromide molecule can affect the nucleophile, we have the water, etc. We did our regular Grignard reagents, and all of this the OTMS just stays where it is. And the correct. The OH could react with the bromine itself, or with the Grignard reagent itself, with that magnesium carbon bonds. Basically, the magnesium would rather react with the OH than it would with the bromine. If you try to make a Grignard reagent without doing this, it's going to just react there, and you're just going to get a deprotonated alcohol. We don't want that.
And the Grignard reagent is the
the Grignard reagent is what we make. This is the Grignard reagent. Adding magnesium to it to do this is making a Grignard reagent, and then the Grignard reaction is when we take this group and let it react with carbon again. Okay, so going back to that was one of our reactions that allows us to add carbons to something.
because then we can like add on where the end is, right?
Correct.
It's more like this carbon attachment magnesium that adds on to the carbonyl carbon.
Okay, so our
regular granular reagent, we had something like ethyl bromide plus magnesium, we get ethyl magnesium bromide, which then if we said that reacted with, say, acetone, these electrons come over here, break that, we wind up adding ethyl group to that middle carbon, so then we have
Why does acetone not like, I know we use it in a version, like, but why does it not break down our skin at all? Or like,
It does. Because our skin is pretty well adapted at protecting us from environmental hazards. So because most of what we think of as our skin is actually dead skin.
Right.
And so we have all those layers of dead skin before you actually get to the pretty sturdy skin underneath that, which then is protecting weaker skin beneath that. So all those layers of skin, they do get taken apart by the acetone, dissolved, and dried out. That's why you actually get acetone on your skin, and your skin was really dry for a little bit, right? Because it does react. And you don't really want to do that too, because acetone's pretty common and it's not super carcinogenic, but it is carcinogenic. So you don't really want to do that. We used to just wash our hands in acetone in the labs.
yeah, because if you got stuff on your hands, instead of we didn't always have gloves around. And so we were just like, oh, I got some stuff on my hands. I'm just gonna wash it off with acetone.
It was different times. And then our last step is always just add water. And it's going to use up any leftover Grignard reagent, leftover magnesium, and it's also going to just protonate this. Okay, so what that other slide was showing,
I'll just recap. The other slide is just showing, okay, if I want to do a Grignard reagent with something that already has alcohol on it,
and I don't want the alcohol to react.
we basically turn the alcohol into something else that won't react. And I did look it up, or the TMS
Trimethyl. The other TMS is tetramethyl. So basically, we're going to make,
and a silane is a molecule that has
silicon in the middle of it, in place for carbon. So trimethylsilane chloride is going to be silicon, CH3, CH3. This is our TMS. So the reason that this works is basically if you do this in the presence of a sterically inert base, sterically inert base is going to pull the hydrogen off. So we're going to get a deprotonated alcohol, which can then just do a SN2. And so we attach this trimethylsilane group to our oxygen. And this is all super unreactive. Basically make it less reactive. Instead of putting an oxygen in between two carbons, put an oxygen in between carbon and a silicon, that makes it even less reactive. So now we've got this big group here that's just going to sit there and not do anything.
and then we have a way of removing it with this TBAF. Which TBAF is that's a good analogy. It's like putting painter's tape on something. It's like masking off the part you don't want to change.
Yeah. Perfect interstate. Do you remember that stuff that we used to advertise in like 2010, 2012, those the frog interstate, yeah. That's all I can remember, that they were just like, it doesn't bleed. Yeah.
So, and then this last step is, it's just a fluoride. We talked about fluoride earlier.
So this, that step,
So this gets us here.
okay, so it's there.
That adds to the protection group. Then we can do whatever we want. In this case, that's the example, they said a Grignard reaction. That's one classic example of when you need protected. And then, the same way that the oxygen displaced the chlorine, fluoride will displace the oxygen. So this is just a source of fluoride ions. That's just gonna come in here, and then you would wind up, our other product would be still our trimethyl silane, just with a fluoride attached instead. And that turns it back to being an oxygen.
So if we were gonna do, so that's like TBA.
That's what TBAF makes. TBAF is a tetrabutyl ammonium chloride.
Tetrabutyl ammonium
Chloride. Basically, something that's not gonna react with a fluoride. And then the fluoride is what comes in. Right?
So if we were gonna do a synthesis reaction and we knew that we started with something that had an OH group and wanted to keep it, even if like we were doing something that we know like isn't gonna react with it, but we didn't know what path we were gonna take at first, could we just do this to protect it for the group and then take it off?
You could, it might be extra steps though.
These are still steps, reactions that are gonna have like their own purifications and like percent yields and things like that. So we don't wanna do that if we don't need to. But anytime you've got something where an oxygen, where an OH group would get in the way, where an OH group would also react. This is a really common way to do it.
And like I said, Grignard reagents are one of the most common ways that we see this. What makes them the most sense is if we didn't have the OH there at all yet. But
Right.
depending on the actual route we're taking and where we had to start, we might not have a choice.
Because once we get here, it'd be actually pretty hard to add anything back in this place. If we just started from here and we're trying to add OH on that carbon specifically, that would be an easy thing to do necessarily.
There's no there's no double bonds to move.
Right. Exactly.
And it's all the way at the end, it's not like substituted basically at all.
Right. So, like, well, I don't really want to have to do the protecting group, but I also don't really want to start without this OH and then have to fix it later.
Yeah.
So the main thing here, like in my experience with this class in particular,
I don't think many of our reactions and many of our synthesis problems do you need to use a protecting group, but I want you to be aware of the idea of a protecting group. And this is like the classic.
We know we started.
no, this is week 9.
And then it'll be OChem 3.
We don't have like a second.
No. Quarters don't give us enough time for that.
Well, physics.
Is Bruce doing his ungrading for physics?
He's doing regular,
It's in regular.
thank God.
I like the idea of having more than just 2 tests. But with a 12-week quarter, it's really hard.
Four exams. God.
That more closely matches what my undergrad was like. We had a lot of midterms. And once a month, you have a test.
Yeah. That makes sense. I feel like I just last one we got filled in. I talked about it, and now it's I don't know what we're like. We are supposed to be studying. What do you mean? We have to do our physics one. It's supposed to be like this Friday. Good, right, it's Friday. Anyways.
Any hoodles. All right. So recap. Here's our oxidation reactions. If we're doing oxidation, we've got chromic acid. The secondary alcohol goes to a ketone. Primary alcohol will go all the way to carboxylic acid. Primary alcohol with PCC or with Desmartin pyridinine or the Swern oxidation. All three of these are options that will take a primary alcohol and stop the aldehyde. The trickiest thing about the Swern oxidation is that it has to be at -78 Celsius. It's a pain, but it's not really going to stand in the way because we know how to do this one. And then the Desmartin pyridinine, I believe the big issue with that is that its yield is just not as good.
We have a video.
Yep. And go back and double check. We first introduced these four reactions last lecture because we went over the specifics.
Yeah.
The other problem with the Desmartin, the pyridinine one, the DMP, is that it was this big honking molecule that we only get to reduce to do one reduction. Well, so the problem with that is it makes it really expensive because that means that you don't get very many moles per gram of that reactant because it has such high molecular weight. And it has lower yields, if I'm remembering correctly, than the other two. So none of these are perfect. PCC is the closest to perfect, except for the fact that we're using a toxic heavy metal that we then have to pay to get rid of or risk getting cancer. DMP is expensive, lower yield, and this last, the DMSO Swern oxidation, has to be at -78 Celsius. And then just to reiterate, since we saw this, remember I used like, we supposed to dichromate to the different alcohols. That was one of our tests in my class when I was in undergrad. And it reacts with phenols too. It'll oxidize the phenol as well. It oxidizes it to this molecule, which is called benzoquinone. Same root, that QWIN, as quinine that you find in tonic water. It's used for treating malaria. Historically, I think we have better options now. Best option is to not get malaria.
Yeah.
But I'm coming from a place of privilege saying that because I've never had to live in sub-Saharan Africa or a place that has lots of malaria infested mosquitoes. It's kind of wild. In the Midwest, they spray pesticides over all of the suburbs in Minneapolis for mosquitoes. They just fly helicopters and planes over them, and they drop this chemical. I don't even know what it is.
They do it here, but they do it more specific. Like they have drones and they have to go out and find bottom water.
Yeah.
And then they go out and they spray.
So
straight as part of it.
Oh yeah. So
It affects the horse community a lot, and we have a lot of standing water on our property for the
right. The Minnesota as a state is one big standing body of water, and so they just do the whole thing. Yeah.
But they find some random big things like out into like and middle of the land, like they will be like, I put mosquitoes, and it's not gonna find water, so then they go out and
Find it.
There's this big thing.
Yeah, we have the resources to be able to do that, and we have a climate where that's effective.
Yeah.
In theory, they didn't used to think DDT was a problem either.
Right. We
But-
should be smoking, it's good for our health.
The stuff that's happening in Nevada is happening out of the movies where it's going to. Just so it doesn't. Great, let's just kill the wildlife, that's something.
Well, and you might not want to hear this, Taylor, but wild horses are not native. They're an invasive species.
Really?
They should not be protected.
Oh, like back in the
Step-
pioneering days?
The Spaniards would go, when they landed, they would release a bunch of pigs, and they would release horses wherever they landed. And so that when they came back to that area, they would have wild horses, and wild pigs. So, yeah, and they took very well to the plains and,
Well, yeah. Very nicely.
yeah. All right. Let's talk about ethers for just a second. We won't go through this whole thing. We'll just go through the naming, because that's something we can cover in 5 minutes.
Since we're already adjusting our, I don't want to get too far behind on the lecture material. So, recap, ethers. Anytime you got an oxygen linking to carbons.
It's considered,
Like, the number two?
Yes.
so if you have a carbon, then an oxygen, then a hydrogen,
That's an alcohol.
if you have a carbon, then an oxygen, then a carbon, that's ether. So, and the way we name these is actually pretty easy. We just look at which side of the molecule is bigger, and we're gonna name the ether with a prefix. Just like it's a branch. Instead of saying methyl group though, we name it. We still use that same, our regular OChem prefixes for how many carbons are on the small side. It's just, instead of it being methyl, we say methox. So if it was just a CH3, we'd say methyl. In this case, it's a methox,
What if it's not a match?
so ethox, propoxy,
So we
butoxy,
just said,
oxy. Instead of adding YL, we added OXY. And you can have cyclic ethers. That's a fairly common thing to see. Where you have an oxygen in as part of a ring structure. That's not uncommon, so we call it a cyclic ether. Naming those gets a little bit different, but don't worry about that, we're not gonna get into that.
So the old school way of naming these,
Was you just name what's on both sides as though it's a branch, so ethyl methyl ether. Okay. Or terbutyl methyl ether. This one actually. I don't know why they put them in this order. Usually you see it as methyl T-butyl ether, which actually is a gasoline.
if you've ever heard of MTBE.
Next time you fill up your car at the gas station, there's a notice on gas station, like one of those Prop 65, this station. Because MTBE is carcinogen, but it also helps engines run better. This is the molecule that they use to get rid of lead in gasoline. They started replacing it with, among other things, TB.
this is
This is the old way.
the, like, as a methyl ether, so there be potassium in between.
Remember, the dashes are our internal way of keeping things. This is, but with everything serving, you know, there's a space.
Yeah.
So especially with ethers and esters, the space is indicating those are two different sides same thing.
So if we add organic,
I'm gonna say, don't use the common names for this. I want you to be aware of it, because like we see this diethyl ether, dimethyl ether. We use diethyl ether in lab all the time, it's solvent, right? But the better way to name these is to use that oxy prefix. So in this case, what's that?
Useful.
This is new school. This is the IUPAC way. This is the real way to do it.
Okay.
So the way that this molecule would have been named previously would have been ethyl pentyl ether. The IUPAC name now is ethoxypentane. So there's our parent molecule, pentane. And then we have this oxygen with 2 carbons. That makes it an ethox. And then just like with normal, we specify where it's attached.
and the oxygen, the ether makes it.
Yeah, the fact it's an ether, so that's why we say ethoxy instead of just ethyl. Good sneeze.
You're fine.
So if we had something like this, it's still an ether because we have an oxygen in between 2 carbons, but it's pretty easy to see that the cyclohexane is the larger side of the molecule. So the parent molecule would just be cyclohexane. And then it's got just a larger side.
The ethyl
It's
of the
ether. Yes. It's a methoxy group because it's oxygen and then 1 carbon. So MTBE was the structure. We'll name this one because this is a good practice one. And then we'll be done for the day. So our parent molecule
is
is terbutyl, but you don't even need to say terbutyl because our longest continuous carbon chain. So it's just propane.
okay.
It's propane that has a methyl group and also has a methoxy group. Right, so when you get the hang of using the ether prefixes, it's just like naming an alkene, really. It's just a different style of branch.
The carbon on the top. Is that mission oxy?
Yeah. So if there was more, if we did that instead, then it would be, everything else would be the same, we would just name it propox.
But why is it a 2 if it's on the other side of the oxygen?
It's on 2 because the oxygen's attached to carbon 2 of our parent molecule. Just like 2-methyl. That's just our looking to say where it is.
Okay. These ones are a little complicated.
They look a little complicated, But as soon as you get the hang of it, it's really, really similar to naming alkanes. Right, it's just an alkane where your branches have this oxy instead of Y.
Yeah.
All right. We'll call it there for today. And then we'll talk about reactions of ethers on Thursday.